of a solid wing. We are not gonna go into the modeling complexity because that's not the topic of this course, modeling, because you can model it on SolidWorks and extract it here. So we will try to simplify the geometry a little bit by having it a solid wing. Solid wings are common in smaller aircraft, for example, UAVs, where you have the wing completely made of foam. So it's a sort of a solid wing. Now, to give it like real aspect, we are going to make the wing swept. I'm looking at the wing here from the top. The root at the chord is 1 meter. The chord at the root is 1 meter. At the tip is 0.4 meter. And the wing has a dihedral angle of 5 degrees. Here I am looking at the wing from the front. The half span is 3 meters. The airfoil of the wing is NECA 2412. And let's say it's made of a very light material, foam, for example. We'll adjust the material as we get into ANSYS. And we are required to do two things. One of them is stress analysis due to pressure on the wing. So we will apply some pressure that will simulate lift and drag, and we will see how it will deform. And we will do something else that we haven't taken in the courses, but it's nice to know about. Something is called model analysis. And before we get into the modeling part, I'd like to just explain what do we mean by model analysis. You guys have taken ODEs, right? Ordinary differential equations. Did you get the word eigenvalues? When I say eigenvalue, do you know what does that mean?
Yes, I took Math 202 and I know it.
Yeah, what does that mean, eigenvalue? Or the characteristic value or natural frequency? All of these, what does that mean?
I remember it, but vaguely, I don't quite remember it. Yeah.
Okay, let me refresh your memory in here. The standard finite element equation F equal Ku, the big one that we're having, F equal Ku, gives me the displacements or the deformation of the wing under a set of external forces, F. But there are situations when the wing is acted upon by oscillating forces. What do you mean by oscillating forces? Forces that change with time. For example, vibration of the wing up and down. If you look from the window when you are in the airplane, you will see the wing moving up and down a little bit. So that comes with a certain frequency. Now, if the applied loads applied with a certain frequency, it turns out that the response of the structure, here it's the wing, or the deformation, the U, the displacement that we're having, tends to increase when this applied load has a certain frequency. And the objective of model analysis is to find these frequencies. We call them the critical frequencies or the natural frequencies. The mathematical term for this is the root square of the eigenvalue. So if we look at the problem that we are having, not a statics problem anymore, it's a dynamics problem. Okay. Now we are not going to have an exam in this. I'm just trying to explain because what does it mean to be model analysis? We are going to do it on ANSYS. You will not feel a difference between it and static. So if I have an applied load, it will cause motion. So Newton's second law will be mass times acceleration. And then I have the elastic forces, the Ku. Okay. In this case, there will be a natural frequency or there will be a frequency of the applied load at which the response or the displacement will have a value. And this value will increase with time. Now, to make this feasible, I'd like to share a small video with you. Let me just share it here to explain what do we mean by natural frequencies and mode shapes. Okay, because once you start do this in ANSYS, it's just like any other problem you have done. It's not an issue, but I want to share this. Do you see my screen? Shabab, I changed
yes,
the
we can
view.
see it.
Yes,
I see. Okay, so what you are seeing here is a bridge that was constructed in the United States in 1940 called the Tacoma Bay Bridge. over Tacoma Bay. Probably have heard of it if you are watching National Geographic. Now, what's unique about this bridge is that it's a clear case of natural frequencies of a structure. The structure in this case is that bridge itself. And people designed the bridge very well, very strong bridge and so on. But it turned out that they didn't calculate the natural frequencies of that bridge correctly, with the result that when they constructed the bridge, the wind flowing over the bridge, which was go back and forth over the bay, had a frequency very close to the natural frequency of the bridge. That means it has an eigenvalue. It has a frequency that's close to the eigenvalue of the ODE of that bridge, if you want to look at it from a math point of view. Whenever you apply a load with this frequency, you are essentially adding energy to the system. So once I run the video, you will see how would the bridge respond to these oscillating loads. These loads are not very high. They are very small loads. These are winds, like right and left. This is a concrete bridge. It shouldn't be affected by wind. But because the frequency, not the magnitude, the frequency of the wind is very close to the natural frequency of the bridge, let's see what happens. This was on the opening day of the bridge, by the way. So that's why you are seeing all these cars. See, this is a very strong bridge. You see what happens? You see in here in the middle? That's a bridge, steel and concrete. And it's responding like this because the wind going right and left, which is a weak wing, but it's exactly at the same natural frequency of that bridge. Okay. And what you are seeing here, what we call the modal shape of that structure. That means how it responds to forces applied with the frequency we're talking about, the natural frequency. So as wind blows at a very low speed, but with this frequency, they keep adding energy and the response will increase. So the U at each point will now increase until, of course, at a certain point, things will break up. Okay. So now you see why we care about natural frequencies and mode shapes whenever we are talking about a structure. You don't want this to happen to wing like this oscillating in the air. Okay. So what happened in there is that the wind blew with this frequency, which is called the critical frequency. And when it's exactly at this frequency, although we have almost zero forces, very small force on the other side, the displacement is not going to be zero. Solving this equation to find omega is what you did in Math 202 when you find the eigenvalue. That was the eigenvalue. That was the lambda. In here we call the root square of lambda, we call it the natural frequency. So back again, the objective of model analysis is to find the critical frequencies of this wing so that we make sure that they are well above the possible frequencies that the wing will be exposed to from air turbulence, from engine, and so on. Is the problem clear?
Yes, it is clear.
Okay. So ANSYS will solve this exactly the same way it solves the static structure. So we will not feel a difference. We will just ask for both solutions. So we will ask, what is the displacement? What's the displacement? What are the stresses due to lift and drag that we'll put? And we will also ask, what is the natural frequency and the mode shapes? So in order to do this, first I need to know how I'm going to draw this simply on ANSYS. What we will do is that we are going to come at the root, then we're going to draw the airfoil, generate a surface. We're going to come at the tip, generate another surface, and then we are going to create the wing in between. So you need the coordinates of the NACA 2412 airfoil. think by now you know where to get this from. You can either draw the airfoil or you can visit one of the airfoil libraries. So I visited here. If you go into airfoil tools, you don't need to do this. I already did, but I'm showing you where to find it. Airfoil tools is one library where you can get all the coordinates and the aerodynamic characteristics of different airfoils. So for NACA 2412 airfoil, it gives you the coordinate X and Y of each of the points of the airfoil so that I can draw the airfoil. Okay, you don't go and look for the equation. It's there. So all I do is I take the data here and I save it in one text file or that file. Now I did this step and I put that file on Blackboard. So I need you to open Blackboard, please, where you find the lectures, and download the file that's called NACA 2412 coordinates because we will use it now. Okay. I'm going to wait for a minute as you do so. Log on to Blackboard. And where did I find it here? Course, and you will find it in the lectures. Down there that you will find the coordinates. NACA 2412 airfoil data file for the exercise. And let me know if you have been successful in locating it so that we can start. I will open the file. Here is how the file should look like. So I got it from airfoil tools, this file. It gives me how to draw the airfoil using like many points, I think 100 points or 200 points. So you see there are 200 points. Each point has a coordinate X, Y, and there is an additional coordinate 0 here because of the Z coordinates. We are telling ANSYS that this is a plane section in the XY plane. We are not doing anything. I'm just explaining the file as you open it. Did you have it, everyone? I need you to download it on your machine anywhere because we will use it now.
Doctor?
Yes.
How can I download it? Because it's just a number.
It's just a what?
A numbers. There's no file.
What do you mean there's no file? Let me put you the file in the...
No, there's no file for PDF files.
It's that file. Okay, let me go and put it for you in our team channel so that you can download it. In the Teams channel in here, I'm gonna upload it. Where's the file? Okay, so let me upload it here. Okay, here it is, the NACA. I think I have it here in the file. Coordinates data. Everyone, all of you cannot download it. We just save it here. Desktop NACA 2412. Okay, so it is there. So let's upload it now. Okay, where is that one? Oh, here it is. Okay, so now you should see it in the Teams channel. Download it from there. If you cannot get it from Blackboard, now you have it. Okay, Shabab. Yeah, sure. Can you confirm you have the file?
Yes, Doctor, we have.
Okay, so let's open now ANSYS, and I will keep the problem that we need to solve here on the side so that we can see it. You can see my screen now. So let's have this here on the side. And what we did is that I want to start first the stress analysis. This is static structure. So if I went here and I dragged static structure. Okay. Let's go into the engineering data. Let's look about the material. Okay. Now, the default material in ANSYS structure is steel, but you can add additional material. So for example, I can go into the engineering data sources, and this was explained also in the previous video. And I can pick a general material, for example. Out of the general material, I can choose anyone in here. I can choose aluminum alloy, for example, and add it to whatever. I can go into the aluminum alloy that I have chosen, this one. And these are the properties that we have. But I don't intend to make it out of aluminum. Let's say I want to make it out of a material that's lighter than this. So instead of the 2770 density, let's say the density is very light. Let's say it's 1,000. It's just as heavy as water now, 1,000 kilogram per meter cube. Okay. Depending on the material, we did not specify one here, but let's put density of material that's much lighter. Okay. So that's for the material. Let's go and have a look at the geometry now. Now, ANSYS had two ways to generate geometry. One of them is space claim, and the other one is using data modeler. Let me see which one did I open. Here, it'll just take a few minutes. If you double click, it will automatically open the space claim. If you double click on the geometry, it is the default geometry generating code in ANSYS. It takes just a few seconds, but don't double click in here because I'd like just to show it to you, and then we'll use the other one. Okay, here's space. Oh, sorry. Let me open the open now. Now, as we're waiting for it to just open, I'd like to show you if you have a SolidWorks and you want to import the geometry right away, so you can get it here if you save your SolidWorks as IGES file. So IGES files are easily transferable on different platforms, so you can upload the geometry right away instead of using the drawing tools of ANSYS. If you are more comfortable with SolidWorks, do it there and save it as IGES. It's taking so much time.
Doctor.
Yes.
For the geometry, we'll use the space claim or designer modeler.
Both are fine. I will use here design modeler, but you can whichever you are more comfortable with. Okay, so that's the space claim, the environment for space claim, where you can crop, extend, do anything that you want. But for here, I will use the design modeler. So I will just close this one. I will go here to geometry, right click, and new design modeler geometry. So let's do this. Both are fine. Depends on what's your preference. Design modeler was the original one that came with ANSYS, but they recently acquired space claim, so they added it as well. So I right click and I open design modeler. Again, in the geometry, we will draw only the wing. It has nothing to do with which type of analysis we'll do. We'll draw an airfoil at the root. We will do an airfoil at the tip. We will loft the wing and that's it. Okay. So here you are in the design modeler. I will draw the airfoil at the root section. So I will draw in the XY plane. Here is my XY plane. And maybe I can look perpendicular to the XY plane to see what's going on. I will create now the airfoil. Now, of course, I can generate points and connect and so on, but since we have all the coordinates in the file, I will go and read our airfoil file. So if you go concept, 3D curve, that means I want to draw a 3D curve because I will be working in space. Now, I need to open it from a coordinate file here on the left. He's asking which coordinate file. Is the screen clear, or do I need? Can you see where I am pointing?
Doctor, what is the previous step you did it?
After opening the design modeler?
Yes.
Okay, so go concept and 3D curve.
Yeah.
Okay, now we are at that point. I'm drawing a 3D curve. Okay, and I want to tell him to read the curve from the file. So I will go to the coordinate file here and I will select a file. If you click here, it will tell you, okay, where do you want to get the file? I will go to your file, the one that you have saved, the NACA 2412. Where did I put it? Here. It depends where you put it in your machine. Just go and select it. NACA file. Here it is. Open. So he now loaded the file and I will generate. Okay. So in the coordinates file, you pick the file from your machine and generate. He drew, but I can't see it because small, so I will just zoom in a little bit. Maybe a little bit more. I think you can see it now in white. That's the airfoil. That he drew the coordinates from the file that we have. This is the NACA 2412 airfoil. Any other type of airfoil, you go and download it from the airfoil tools and you use it here. Okay, up to this point. But this is just the curve now. I need to create a surface because I need to generate the solids out of here. So what I will do, I will go to concept and I will create surface from edges. I need to create a surface from this edge. So he's asking where are the edges? I will click on the edge, apply, generate. Now I have the surface of the airfoil. If you haven't seen this, we are going to do it again on the other wing, on the other airfoil on the tip. Okay, so what we did is we said concept, surface from edges. We pick the surface, we pick the edges, apply, and generate. Okay, now if I look in 3D, you will see this is the airfoil at the roots. Now I need to do the same at the tip, but with a smaller airfoil. So what I will do, first I have to move my drawing pen to the other plane in here. So we will create a new plane. That's like at a 3 meters from the first plane. This is where we draw our first airfoil at the root. I will create another plane to draw on at the tip here, 3 meters away, and I will draw the other airfoil. So in order to create the plane, you see this simple here, it's new plane, creating a new plane. So I'd like to create a new plane so that I can start drawing there. Where do you want the new plane? I want to draw it at an offset of z, right? If this is the z coordinate, I want my new plane to be 3 meters away from this plane. I can draw it either to the left or to the right, z positive or negative. So I will put it as negative because I want to draw it just like this one on my right. I'll put z here is -3. That means I want another plane that's -3 meters from this one. Not only that, you see this leading edge and this leading edge of the wing, they are not aligned because I have a dihedral angle. So I'd like the leading edge of the other wing to be a little bit above the horizontal to simulate this dihedral angle. So this point is at 3 meters in the z direction, and that distance here should correspond to 3 meters tan 5 degrees, which would be a small value. I think 3 meters tan 5 degrees is 0.25. So I need to raise that point in the y direction. So I have an offset in the y direction, offset y of 0.2526 or 2625. I'm sorry. What are these numbers? What are these three numbers? You see this point relative to this point is 3 and 0.25 to simulate the 5 degrees and the 3 meters in here. Okay. Are you following? Can you perform this on your machine? Minus 3 meter because I want to draw it to the right, opposite to the z. Of course, you can put it 3, but you will be drawing the other half of the wing, the left half, which is just fine. Okay. So now I have that plane in there, and I will generate. My plane is ready. And you see, since we have XY plane, Z, X, Y, Z, he generated a new plane, called it plane 4. That's the one I'm interested in. I'm going to click on that plane 4 so that I can start drawing. So in plane 4, what do you want to draw?
Doctor,
yes.
What did you choose the second transformation?
These values?
The second offset about Z or about what?
Well, the first one would offset Z. That means this origin will move in the Z direction with a distance of 3. So
Okay.
that's the first transformation. And I chose it minus 3 because you see Z is pointing to the left, and I want to draw my other plane here on the right.
Okay.
So I put Z minus 3. For the Y, this point or any point in the airfoil, I want it to move up to simulate the 5 degrees. So it's an offset Y of 3 times tan 5, which should be 0.26. Okay.
Okay. Clear.
So, and I created generate. It's not there until you click generate. So when I click generate, he created plane 4. So now I am in plane 4, and I will repeat what I did to draw the airfoil. So that means I will concept 3D curve, and I will choose not a point. I will choose from a coordinate file because I have a coordinate file, and I will select my coordinate file as the NACA 2412, exactly the same file that we have. So many files here. Okay, here it is. Open and generate. So if I zoom in now, you see what happened. This is the first airfoil that we have drawn. It's an edge and a surface. This is the plane that we have created, plane 4. And here is the airfoil that we have drawn now. It's still an edge. Now you realize that both of them are the same size because the coordinates that we get from any airfoil library is always giving you a chord length of 1. But we know we can adjust this now. I can scale this and make it smaller. Okay. So let's first create the surface. So I have now a curve. So I will create the surface in the middle. Then I will make it smaller. So I will go to the concept, surface from edges, just like I did in here. Exactly. I'm just repeating. It is my edge, apply, generate. So now I have 2 identical airfoils. Now you can argue I don't have to do this. I could have taken this and copied it through a distance of 3. Yes, you can do. That's perfectly fine. I'm just trying to remind you of how to read from the file. We can copy it, of course. Now what we will do, this airfoil should not have a chord of 1. It should have a chord of 0.4. So I'm going to scale it down. So I will go to create body transformation. Here where you can rotate, mirror, cut, move, scale. So I will go create body transformation, and I'm going to scale. What do you want to scale? I'm gonna scale that surface that I have. So I will apply. Now I pick the surface. I have to tell him what's the scale ratio. Do you want to make it bigger or smaller? So I will scale it with a factor of 0.4. I want to make it smaller with a factor of 0.4. And where do you want to scale it about? I can make it 0.4 and maintain the leading edge in here, or maintain the trailing edge in here, or I can scale them relative to the origin. Where do you want to scale it around? When you scale, I have to scale around a point. So where is the origin? I will say, I will pick a point to scale about. You see here, I want this point to remain the same. So I want to scale the whole airfoil around the leading edge. So that's why I select the scaling origin. I choose a point, and with the point, I will select that point in here. The point that we're having, the base point is that point. Why that point? Because I want to become shorter around that point. So it will end here, for example. If the trailing edge was the same, I will pick at the trailing edge. But here it's only the leading edge. Apply, generate. So here you go. I have now two airfoils. One of them is 1, the other one is 0.4. They both have the same line for the leading edge. And now I can loft the surface around it. I'm going to stop for a second to see if you have questions. Again, everything we're doing here has nothing to do with the finite element method. We are just modeling it. The finite element method will start once we are done with the model and start putting the loads. Okay, two airfoils, 1 and 0.4. Okay, any questions? شباب, any questions?
دكتور،
Yes.
أنا عندي النقطة اللي اختار الفايل عشان أحط هذا، وقفت.
هنا؟
لا قبل في البداية.
تختار الفايل هنا عند الايرفويل الثاني طيب ولا الأول؟
الأول.
لا الأول it's very far, so can you see the video later on and follow up with us?
Okay.
لأنه ده يعني قبليها I cannot even go back here. طب خلينا did you open the file? Did you select the file?
Yes, I select the file, but it didn't appear.
Did you click generate?
Okay, I have to generate.
click generate. وبعدين zoom around the origin, اختار الزوم كده واعمل زوم عليها عشان تكبر لان هتلاقي الشكل عندك صغير. should see the airfoil.
zoom out أو zoom in؟
لا zoom in, يعني افتح زوم ويندو كده وبص عليها وشوفها.
ايه طلع.
تمام. طيب بعدين هتروح تقول له concept.
اروح concept.
surface from edges.
اوكي.
وبيك الايرفويل. apply generate.
اضغط عليه يعني.
اختاره الاول. ايوه كليك عليه اختار.
أيوة.
وبعدين كليك ابلاي تحت هنا، تلاقي تحت هنا في ابلاي.
اوكي.
وبعدين جنريت. ابلاي معناها ان انت بتكونفيرم الاختيار بتاع الفايل and then you click generate. كده عمل السيرفس صح؟
ايوه.
اوكي خلاص. now we need to create the plane. So البلين اللي on the other end. So if you click here create new plane.
اوكي.
Okay. When you click a new plane هتيجي تختار في الترانسفورميشن تحت where do you want to create. هتختار من الجنب هنا offset z لان انا عايز اعمل transformation in this direction. offset z -3. Did you do this?
اوكي.
بعدين هيطلع لك حاجه second transformation. هتختار offset y 0.26. Okay.
value 2
and generate.
ما طلع لي value 2.
خلاص. خلينا نشوف، نحاول اصغر الفيو اللي هنا. نسيت.
اسوي generate صح؟
خلاص. ها سويتها ولا لسه؟
دكتور انا سويت الفاليو 2 اللي هو offset y. اوكي.
generated ولا لسه؟
لا باقي. حطيت الاوفست y 0.2625 بعدين اسوي generate على طول.
ايوه بعدين generate.
اوكي سويت.
هتلاقي ظهر عندك في الليفت فوق plane 4 اتعمل خلاص رايت.
كيف اقدر اشوف البلين 2؟
لا بس ما هتلاقيه ما ظاهر عندك في التري اللي على الجنب. there is a tree على الجنب في الكورنر فوق اللي هي مكتوب فيها اكس واي بلين زي اكس بلين واي زي بلين كيرف 1 سيرف 1 وهتلاقي فيها بلين 4 رايت.
هي بلين 4.
كويس. كليك على بلين 4 just one click معناه ان everything will be drawn now will be drawn in plane 4. انت لسه ما رسمتش حاجه فمش هتشوف حاجه. and you will repeat the same thing we did في الاول. يعني ايه؟ you will read the file, create the edges, create the surfaces. تمام. فخليك بقى انت تعملها عشان continue ايه ال remaining steps. وده هيديك الايرفويل التاني اللي انت شايفه on the other side. خليني بس شير. ها خلاص. did you do it? repeat the whole thing at the other plane عشان we can go on. It's in here. Okay, so I will go on with this now. Okay, so we have two airfoils now. All I have to do now is to cover them on the skin. This is done by what we call lofting in here. So if you click on skin loft, okay. Skin in here. What are the airfoils that you want to loft? I will choose this airfoil, and with control, I will pick the other one. I need to pick both of them. So I'm using my control. These two, apply and generate. Now you have seen the one. So what did I do? Skin, loft, click first, airfoil, second, apply, generate. I'm picking both of them, the small one here and the big one. Now you can see now I have the full wing. It's a solid wing, but it's just geometry. We haven't meshed or did anything yet. Okay, so you can look at it from the Z. Here is the airfoil. This is the root section. Here is the tip section. I can look at it from here. You can see the dihedral angle, the 5 degrees. This is the plane 1. This is plane 4. And if you look at it from the top, this is my wing. The leading edge is straight and the trailing edge is inclined. This length is 1, this is 0.4, and this is 3.
Doctor.
Yes.
Can you repeat the last step because I had some issue with my.
Do you have the two airfoils? Let me show it in here in 3D. Did you have the two airfoils?
Yes, I have them.
Okay, so you go click on skin loft. So all he needs to know what are your two airfoils to loft between. So you will pick the small surface while pressing on control, and then you will pick the other one. So I need to pick two of them, the small one here and the big one here, and you click apply. Because it requires two selections to loft. I need to cover surface between two ends. So here is the first end. Don't pick the big one, of course, the small one, and the big one here. Click apply and then generate. You should get that one.
Okay, I got it. Thank you, Doctor.
Now we are ready now to start finite element. The point is, if you look in here, what did we generate? He generated like a line body, a surface, a line body, a surface, and our solid. This is our solid in here. But if you go and meshing, if he meshes the line bodies, it's gonna cause problems. So typically, we want to suppress these, just keep the solid. This is our end result. We want to erase everything else here. We really don't need it so that they don't interfere with the mesh. So if I go in here, if I connect these and right click, I am gonna suppress them. Suppress these, that means please don't include them in your mesh. All I need is just the solid that I have generated in the end. So I selected them, right click, and I just suppress the bodies. Now I'm ready. If you go on the workbench, you see the material is okay, the geometry is now okay. Now we are ready to double click here and put the model. By the model, we mean the loads, the supports, and looking for the results. So this will open the mechanical. Takes a few seconds just to open the model. Just give it a few seconds. Here it is. So that's the mechanical. And what you are seeing now, he's reading the geometry from the design modeler. Now, you can skip everything we did here up to this point if you want to draw it in SolidWorks. If you can draw this wing in SolidWorks, go ahead and do it. Okay, you have the coordinate system, draw it in there and upload it into the geometry as IGES, and we can start from here. So actually the modeling part starts from here. The ANSYS starts from here. Everything before was just drawing. So I don't need any more to see the problem. I have it in here, so I'll just enlarge this one. You see the geometry is ticked correct, material is correct. The mesh is not, that means we didn't mesh. So I will right click and generate mesh. If I were you, I would not change the mesh size because it will take a lot of time. And you see now the mesh consists of solid elements. Each one of them has 8 nodes, except the one at the trailing edge here has 6 nodes. This element has 6 nodes only. So each element in here would have 24 by 24 stiffness matrix. So you can imagine the size of the full stiffness matrix in here. Now what remains is to define the supports as well as the loads. Let's start with the supports. This wing, I will say it's fixed on this side. So I will go and right click on static structure, insert a support. Now I have all these kinds of supports to choose from. I will choose a fixed support. And where do you want to apply the fixed support? I will choose all the points on this surface, apply, and that's it. Every single point here now is a fixed support. If I want to put a distributed load on the wing that I have, then I will go and right click, insert pressure. I can select all the surfaces that I have in here, and I can put a pressure value. If you put it positive, it will be normal to the surface, into the surface. If you put it negative, it will be out of the surface. Now, maybe I don't want to put it as a force like this. Maybe I want to put it with component, just lift and drag. So I will go in here, not normal to, I will choose with components. When I put it in components, I will say I need, for example, I'll just pick random numbers, 0.1 megapascal in the X direction. That would be the drag direction. Maybe I will make it even smaller, 0.01 megapascal, and maybe 0.1 megapascal in the Y direction, the left direction. So that's the distributed load that I'm having. Okay. So now we have the value of the pressure. Now you see he didn't generate the pressure. I still have here a question mark. That means there's something wrong. I didn't pick the geometry. I clicked it here, but I didn't apply it. Now it's there. Okay. So the pressure that we have in here has two components. It has a component 0.1 in the vertical direction, in the Y direction, a component of 0.01 in the drag direction, which is the X direction. So I have supports, I have loads, everything is ready. I can right click and solve. What's happening right now? He's constructing the stiffness matrices based on all the coordinates, rearranging, getting the equations where we know the external forces. Remember, every single point here, we know the external force from the pressure. He's solving for the displacements. Then he's substituting back U into the stiffness matrix to find the support reactions at these points of the supports, exactly as we did in the simple truss problems. Now you see the tick here, solution is complete. It's all in the database, but I didn't ask to see it. Let's start seeing it. So I will generate a display tool. I right click, insert deformation on the solution, insert deformation total. I want to see the total deformation. I also want to see some stresses. So insert stress. You can see the maximum principle here, which is sigma 1 Morse, the one that you get from Morse circle, maximum stress, minimum stress. Or we can see what's called the von Mises stress, which is a way to represent the combined loading. If you want to see the shears only, so I will see the shear stress, and so on. So you see all these are visualizing tools so that I can read from the database. To make them active, right click, evaluate all results. Now he's reading them from the result database. What do you want to see? Do you want to see the total deformation? So I will click on it. That's the total deformation. It's given in terms of values in here as colored. So you see the displacement here is 0. The displacement increases in values until you get at the end, and you realize the units here is in millimeter. Is presenting the result is in millimeter. So the tip will move up with a distance of 158 millimeter total. If you want to see it from the side, here is how it's gonna look like. If you want to see how the wing is gonna deform from the no load up to the load, we activate the animation. So animation here, down here, if you just click on it, it shows you how it bends. The lower surface is the no load situation. The upper surface is the full load situation. So it will bend upward. It's not going to oscillate. This is just deceiving, but he's showing you how it will bend upward. Okay, I will stop it. It's just fancy, but it doesn't have like a real meaning. So the maximum is 158 millimeter upward. That's the tip. If you want to look at the stresses, I will click on the equivalent stress. Here are the stresses. You see, if you take any section of the wing, let's say I will take that section and I look at it here, you will see the stresses maximum on the top, maximum on the bottom, 0 in the middle. The 0 is the blue one. And he's showing me here the maximum stress is 530 and the unit is megapascal, 530 megapascal. Now, you also see that the maximum stress in here is more than here, and it gets smaller as you get out, which makes sense because the bending moment in the outside is 0. As you move in, the bending moment increases. So I expect the stress here to be more, increases until you get to the root section. Where is the maximum stress? It should be at the highest point from the centroid, right? Where is the highest point? That's not the point, or this, it's the one that in here, and that's true. That's the highest point of the centroid. These 2 points in here where I have the maximum stress. So it's very important to look at the results after we do it and see if they make sense or not. Maybe I did a mistake. Let's see the shear stress. Now the shear stress is very small because the pressure is very small. It just gets, it has some value very close to the supports as well. Okay. And you can add anything that you want. Maybe I want to see the normal stress only, for example. Let me do this. Evaluate all results. Have a look at the normal stress. Here is the normal stress, very small value. But if you look at it across the section, and let me zoom in a little bit, you will see that I'm having a compression on the upper surface and tension in the lower surface. Compression, minus sign, and tension, the plus 2 to 1 on the lower surface. And you can see the gradual variation between the compression and the tension, which is the bending stress distribution we are accustomed to, the sigma, right? Sigma is linear, change from maximum positive to maximum negative, and it's 0 in the middle. 0 here is the green one, right? The boundary here is the 0. So that's, you can see this is as like the neutral line of the wing. Okay. Any questions up to this point? Where we did the, what we have done here is the static analysis of the wing. We have found the stresses, any type of stresses, under the effect of a lift and drag load. Okay. Any questions? So if you missed one step or so, you can go back and watch the video and do it again. Okay, now let me do the second part. The second part here, for the same wing, I need to do the model analysis. Tell me what are the natural frequencies of this wing. So what I will do, I will go back to my workbench, and now I want to do a different type of analysis. This is analysis that we didn't do before. It's called model analysis. It's somewhere in here. Here it is. Model. So for model, I will drag it. I'm gonna drop it here. That's another type of analysis. And rather than going and drawing the whole thing again, all I have to do is to tell ANSYS, please take the previous geometry and use it here. So that means everything I did in drawing the airfoil, the surfaces, will be used here in my new project. So I don't have to worry about drawing again, but I will go to the model and I will put the boundary conditions or the supports, as well as asking for the modes to be calculated. So I'm clicking here now on the model. So here it is. He's reading the geometry. Give me the geometry. So you realize we don't have the external loads. We don't have the supports. I need to put them again if I need. Now in model analysis, as you can see here, the external load is 0. So there is no external load. The bridge, when it broke, it was under a very small load. Okay, but the supports need to be defined. So I will define the supports. I will right click, insert, support, which is a fixed support, add this boundary and apply. That's it. I don't need to put the external loads. So in model analysis type, this is the model analysis type. This is the static. In static, just like the problem we are solving by hand in class, I need to apply external load. These are the forces, 2,000 pounds, 3,000 pounds, and so on. But in model, We don't do this. It's just like in your ODE, the left-hand side of, or the right-hand side of the equation is 0. We want to find the natural frequencies without external load. So if I come in here, I put the supports, no external load, and I am just meshing. We need to mesh it, generate the mesh. So he's meshing it, and I am solving. What do you mean by solving for model analysis? That means I'm asking what are the natural frequencies? What's the critical frequencies of this structure? Okay. So now what he's doing, he is solving this equation in here. He's trying to find what are the values of omega, and for each one of them, what is the displacement u? How would the beam bend under these natural frequencies? Here are the results. He told me the first natural frequency, number 1, is 12.9 hertz. So this wing will start having a great magnitude of oscillations if the applied load has a frequency of almost 13 hertz. If the load is 14 hertz or 15 or 16 or 17, the response will not be that high until the applied load has a frequency of 49 hertz. So the second natural frequency is 49, the third is 98, and so on. Okay, so he's giving me the first 6. Of course, there are more frequencies than this, but an engineer would be interested mainly on the first or the second natural frequency, because I want to ensure the safety up to first or second natural frequency. I'm gonna choose all of them, and I'm gonna ask, create the mode shape. What do you mean by creating the mode shapes? It means you told me now the natural frequency. Tell me what are the U's, the displacements that correspond to this natural frequency. How would this wing bend under these with these frequencies? So mathematically, omega is the natural frequency, and U, or the eigenvalue, and U is the eigenvector. Probably heard the name, the eigenvector. Okay, so eigenvector or the mode shape is what we get for each frequency. I have 6 natural frequencies. He gave me 6 mode shapes, and I'm going to right click, evaluate all results. So what do we have here? I have shapes of how would the wing respond if the applied load has a frequency of any one of these: 13 hertz, 49 hertz, 98, 115, and so on. But in between, the response will be minimal. It will not be an issue. Let's start seeing them. If I pick the first one, for example, and I want to see the total deformation of the first one, this is how it looks like. Now, this is actual oscillation because it's with frequency. So you see, it's a bending mode. It will bend up and down. So if the external oscillation with a frequency of 13, it will bend up and down. Okay. What if the external oscillation is the second mode, 49 hertz? You see how it looks like? It's still bending, but it's not up and down. Let's have a look at it from here. You see how it's going to bend? It's not only half a wave of bending. No, it's one whole wave of bending. Okay, let's see the third mode. That's the third mode. You see the third mode? It's not bending up or down. It's bending forward and aft in the X direction. If I look at it from the top, you see that's the mode. It's bending forward and aft, forward and aft. When will the wing oscillate like this? If the applied load has a natural frequency of the third one, 98. Let's see the fourth one. And oscillate. That doesn't seem like bending up or down or right or left. This more like twisting. The wing will twist. This is very similar to the natural frequency of the bridge that we have seen when it broke. It was twisting mode like this. If I look at it from here, you'll see how it's twisted. Just like the bridge when it collapsed. And the fifth run that one. Again, it's a twisting mode. The fifth is also a twisting mode. Like this. And the sixth, and so on. You can continue. Actually, we can ask for more than 6. We can have 10 or 12 or whatever. But typically, if the structure is safe for the lowest natural frequency, the 13, it will be safe for the other ones. Not needed there. So let me run just for fun. This is the 6 mode shape that we are having. 2 full waves on the structure. You see this point does not move. These points move. The U's are calculated in here. Okay. So you have seen now how the finite element method can be used to solve either static problems, F equal KU, which is the first problem that we had, this one. This is, and that's the bending mode. This is F equal KU, finding the bending of the wing, maximum displacement. And it can be used to find the natural frequencies and the mode shapes of a wing. Now, we did it for a wing. You can do it for a part of a machine. We can do it for a car. We can do it for a fuselage. Every structure has natural frequencies and mode shapes. Okay, I can see you might have missed some points in there. So I'll make sure you have the recording so that you can finish the exercise. And just like the other 2 exercises, we'll need the link to the project file. Let me show you where do you save it. Here it is. When you save a project file, it saves, where is the wing problem? It saves a workbench file, and it saves a folder that contains all the files of that workbench. So you see, for example, here truss, you will see truss files. You will see plate hole thermal, you will see plate hole thermal files. So you pick your 2 and put them in any link on any cloud storage and send me the link for that one so that I can see it. Okay, Shabab? Let's see. Now, when do you think you can submit this one? Yeah, the ones we had yesterday are due today. When do you think you can submit this one? Will we say Saturday? It's fine.
Doctor, you mean this exercise or the?
Yes. Yeah. This one. This exercise.
Make it Saturday.
Saturday. Okay. It should. You see, watching itself will takes about an hour, but doing it will probably take you like 20 minutes. So let's say Saturday, you can send this. So inshallah, Sunday and Monday, we will be having 2 review sessions before the final exam. On Saturday evening, I'm going to post a time slot on Saturday evening to account for the class that we missed on Monday. You don't need to be there unless you have questions. I will be available on the Teams. I will open it. I'll be there if you have questions, either on the ANSYS, either on the finite element, or as you study for the quiz, quiz and final exam. Any questions that you will have. Okay, I'll post exactly what time on Saturday evening, just to make that time slot that we missed.
Doctor,
if you have problems in doing the exercise, just let me know early so that we can address these problems. Yes.
there is no more exercise on ANSI, yes?
Yes, there is no more one on ANSYS. This is the last one.
Okay, thank you.
Okay.
Doctor, it's for the yesterday exercise will be today in the midnight.
Yes, correct.
I should
Also, if
put it in Drive and send the link.
just the link, yeah.
But I after I finish it, it will be like a file. I put the file in the Drive and
Yeah, send me the link to the
send the
file
link.
so that I can see it. Yeah, if you send me the link, I will be able to see the file. Okay.
طيب دكتور اللينك ارسلها لك ايميل ولا؟
لا انا هعملها على البلاك بورد. I will open it as an assignment. So you will submit the link على البلاك بورد كأنك بتسلم homework عادي يعني.
اوكي.
Okay. So I'll make one for today and one on Saturday, inshallah, so that you can put it there. تمام؟ واضح كده؟ Now, I want you to remind you of the quiz that we're having on Sunday. This is like a simple finite element problem that we can solve by hand. Of course, these problems we had an answer is very big, but the ones that by hand, like the trusses, as you do the homework, you realize we already solved one of them. I gave you the answers for one of the two homework problems so that you can follow exactly that on the second one, the second problem. So make sure you finish the bonus homework, attend the bonus quiz. Typically, finite element problems are easy to solve. They just need to be like systematic. You don't know mistakes in multiplication, addition of the matrices, and so on. So when is that? I think it's Sunday, right? That's on Sunday. Then we are going to have a review session as well as on Monday as well. Okay, so the time frame, okay, with everyone, you are
Yes,
you
thank
know what to expect. Okay, one last thing. I keep getting messages from the registrar every day with the number of students who filled the evaluation. Every instructor gets this for courses, and I have only 4 students who filled the evaluation, and somehow they want us to remind you to fill that. So please, in the remaining 2 or 3 minutes, log into the portal and fill the instructor evaluation for all your courses, not just 3 to 8. If you haven't filled it for math course or any, please log on and do this, because providing a feedback is important for everyone to get your feedback for improvements in the future. So please do this. It will not take you much time, but do it for all your courses. It's you log done. So I'm going to leave the remaining 5 minutes for you to do so. I think the deadline is tomorrow or something. Okay. Since we have a few minutes, maybe you can do this now. Okay.
Doctor.
Yes.
Doctor, I have a question on exercise 2.
Yes.
When I press solve, I get message that there is an error. I don't know the issue.
What does the message say about the error? Can you send me the error message so that I can help you with?
Can I read it now or?
Yeah. Send it to me now. Send it to me, and I will look at it and get back to you. But you mean the exercise of the plates or the truss?
Of the plate.
The plate. Okay.
Yes.
Most probably you missed one of the supports. This is a common message if you missed a support condition. So if you send me the error message as well as the link to your file, put your file in a cloud, and I will access it and tell you where exactly is the problem.
Okay.
But send it by email now, not for so that we can finish it before you submit the final one. If this is the one that you want to submit.
Should I send the message by WhatsApp now just to see it?
Yeah, the message is a small thing, but the file itself, you will not be able to send it. So just send me the link to the file. Yes.
Okay.
Okay, Shabab. So I will leave now. Please take the remaining 2 minutes to fill the evaluations for all your courses, and I will see you, inshallah, on if you have questions on Saturday evening. I'll post the time slot, and we'll meet on Sunday for the quiz and review. Thank you, Shabab.